anyways. I don't know why. Okay, so uh, okay, what I was saying is, so we describe that just like in harmonic oscillator problem, we can set up the full state space, or at least one complete set of states, which is a common eigenstate of the number of the A dagger A operator, which is, we should not call it a number operator, but we call it from this analogy because it doesn't actually say number, but it's tell you which state you are at. So we found the common eigenstate of that operator and the Hamiltonian operator, which is the states, harmonic oscillator states, and we found a way to commute between them, which is this A dagger A operator. So we just want to do the same thing here, because it is also same similar prescription, which is a where you construct the Fock space states in terms of number of particle, and you want a machinery to commute between the states of this Fock space. So that is what I described last time, and I said that there is this operator. So we started with an operator which we called, let's say there is a pair of operator, what kind of mathematical property they will have if they commute. So the pair of operator is given by A dagger A, and they satisfy this property of commutator, and then there is a number operator. Then I showed that this operator must have the property, if it has a eigenvector and eigenvalue, then the eigenvalue must be greater than equal to 0, and the 0 implies the corresponding null state or corresponding eigenstate, which is equivalent to the 0 eigenvalue, will have the property that A phi is equal to 0. So the A operator, whatever it is, I have not yet described it as a number, as a anything, but I'm just saying, let's say this is the mathematical property, and if it acts on phi, and of course the analogy and the inspiration is all coming from harmonic oscillator, but just to say that if that operator acts on phi, it will give me 0. So I identified the property of the state, which is the lowest energy. So we found that the lowest energy must be 0, because it cannot go below 0, and the property of that state will be, if I act A on that, it will give me 0. And remember, this was something we were confused about, at least I was confused about, you guys were not, that that I was trying to argue this something else, but that is for harmonic oscillator. But and found, you told me that this A phi has to be 0. Okay. Okay, so now we wanted to see, next question we want to ask, that if this is the property of the A operator, then what is the what is the property of this chi operator, which is chi is nothing but A phi. So then we found, using the commutation relation between n and A, that if A phi is a eigenvalue, if phi is a eigenvalue of n operator with with if A phi is a eigenstate of the n operator with eigenvalue, sorry, I'm mixing up. If phi is an eigen, if phi is a eigen, this is the 830 effect. If phi is the eigenvector of n operator with phi eigenvalue, then A phi is the eigenvector of n operator with phi minus 1 eigenvalue. So that means if you act on A phi, if you act A on phi, you can go one integer level below. I have not yet stated anything about phi. I don't know if phi is an integer, but phi minus 1 is one integer down eigenvalue. So it is very similar to the harmonic oscillator case. And I asked you to prove this, which is very simple if you got this proof. It's just opposite way. Okay. So up to this, what we talked about last time. And now we want to say that what else we can say about these operators. Okay. Everything was fine up to this. Okay, I assume it was fine. So now let's move on to study the further the property of. So the main point is A dagger is equal to 1, n is A dagger A, then n will have a eigenstate. If that exists, then phi must be greater or equal to 0, and the state, if I call this state phi 0, which is n phi 0 is 0, then it must have the property, there must be a state which give me this. Okay. And similar, we found further using a combination of these two, we found in A phi must be phi minus 1 a phi. This is all we did so far. Okay. And similarly in a dagger phi, okay. So now let's argue that what kind of property of this operator should have. Let me write just a second. Okay, I jumbled the pages of my note. Okay, let me open it in the screen. Yeah. Okay. So now let's try to find that what are the property of the smallest eigenvector. So let's say I have the smallest eigenvector phi naught, or eigenvalue phi naught, and value phi naught eigenvector phi naught kate. So this, let's call it the smallest. So it must satisfy that following. This is an argument that such a eigenstate exists. And so if psi is a phi naught, okay, and if psi is not the null vector, then n psi must satisfy phi naught minus 1 psi. Okay. So that means phi naught minus 1 has to be an eigenvalue. But we know that a phi naught is equal to 0, and that came from this point. So that means the only way you can interpret it, this going to negative. So a phi naught equal to 0. This implies a phi naught mod square equal to 0, and that implies phi naught in phi naught equal to 0. So that means this has to be a 0, its eigenvalue has to be 0. Okay. So that establishes that phi naught is definitely 0, and we call this phi naught state as the 0 state, okay, which satisfy all this property. So n, if you apply n on that, you will get 0. So that's why I call it, I will connect it with the 0 particle state, but let's just think it as a mathematical problem. Okay.
So you said phi naught minus 1 must be an eigenvalue.
Yes.
And then what did you do?
Yeah, so what I'm trying to say here, that phi naught minus 1, so this is where what I'm trying to argue here, that if this state must have the property that it will give me 0. So I'm trying to argue this by saying, earlier I showed that a phi naught must be equal to 0. So that
Yeah.
leads to eventually that the n cap, this eigenvalue phi naught, has to be a 0.
Okay, okay, okay.
Uh-huh.
It's like the 0 point energy argument.
Yeah, it is like the 0 point energy, but I'm not, I everything inspired from that, but I am pretending that I am developing this as an independent thing. Okay, because this is not exactly the same thing. I'm just saying let there be an operator, what kind of property they will have. Okay.
Sure. Yeah.
Okay. So now what I'll try to show, what happens if you act a dagger. Okay. So now consider in a dagger 0. So we know in a dagger 0 plus a dagger in. I can rewrite this as in this form. Now this must be in a dagger 0, because this is 0. So that means this is nothing. So the purpose of doing all that is to take the n on this side, so such that I can act it, because I don't know yet how the a dagger is going to act on 0. Okay. I know the property of n a dagger. I know the property of a dagger n. I know the property of n0, so that's why I want to push the n in this side. So in order to do that, so if you see this proof, you will just see, okay, this step if you do, you will get this result. But I want to convert this expression in terms of what I know. So what I know is how n acts on a. So in order to do that, I have to use this commutator, and then I end up in this form. But I also know what is this, and this guy is nothing but a dagger 0. So that means in a dagger 0 is 1 a dagger 0. That means if n acting on a0, which means on the ground state, or n acting on 0 gives me 0 eigenvalue, n acting on a dagger 0 will give me 1 eigenvalue. Okay? So I can call this state the 1 state. So let me write it in this way, but there is a normalization which I have to think about also. And it must have the property which is trivial to see. Now I know why I'm not writing any normalization, because a dagger 0 is equal to 1. This is coming simply from the fact that 0 in sorry, this is coming from the point that, yeah, so this is coming from the point that a dagger 0 is 1 and 1 is 1. Okay, so now, so you can also show it from here, because what I was trying to say that 0 a dagger is 0, which, but you know that a dagger a, so if you shuffle it, this will give you 1 and this will also give you 1, or alternatively you can do it in this way. You can shuffle it and write it as 1 plus a dagger 0, sorry, a dagger a 0. So that will give me 0 1 0 plus 0 a dagger a 0. So this is 1, and this guy acting on 0 is simply 0, so it is 1. There's two ways of showing it. Okay, now, so this part will be a bit heavy in algebra, not that heavy, it's very small one line algebra, but you have to sit down and do it. You may not follow everything in real time, but even if you are not following every step in real time, at least understand, try to understand, or if you don't understand, then stop me and ask that where I'm heading and what is the agenda overall. Okay, so these small sub steps you have to sit down. It's not everyone can follow it if you are not well versed to it. Yeah, somebody asking
Yeah,
something.
yeah. How did you write that thing? A dagger acting on zero. That mod square is equal to one. You said. I mean,
Yeah,
do we have this information a priori?
no, I'm just writing this, and I'm showing that this means this, and how it is happening, that I'm showing here.
Okay, okay.
Hmm? So now I will demand this always, and in order to demand that, I have to do something, which is, because I'm just demanding all the states are normalized. So that is what I'll do. Okay? So let's see one more example, then you will understand. So now this one is so now let's say I have a state 2, which is a dagger 1. Okay? I don't know yet what is the factor. Now I demand this. Okay? Now let's see where that demand takes us. It means a dagger 1 mod is equal to 1, which means 1 a dagger 1. Sorry, this is, so I want to evaluate this quantity. I don't know yet this quantity. I will see what I have to do in order to fix that. So this quantity is this, and this is nothing but 1 a dagger 1 1 a dagger a plus 1 1, that is 2, right? So that means my 2 must be 1 by root 2 a dagger 1. If this is true, because if I write it directly, then it is equal to 2. So I readjust the definition by putting a root 2 such that this is always true. This is we demand. And we redefine it with this factor. Is it clear? Are you following this point?
Yes, sir.
Okay. Okay, Nilanjana, is it clear to you?
Yes, Abid. I am checking once again.
Yeah.
I
So
mean, I
now,
understand 1/√2, but that there's like mathematical problem.
okay,
I
just the
understand the
point
problem.
is I adjust all the definition in a way such that all my states are normalized. So now you can do this exercise and show. Now this is something, it's not new actually. This we have seen already, all these things. So this will be my n plus 1 state. How I get n plus 1 state from n. So now that means I can write the nth state as a dagger to the power n acting on 0. N times I act on 0, I reach on n, right? Square root n factorial. So check these two steps. This is nothing but a iterative formula. Just do it multiple times. You will see this formula is emerging. So now what does it tell me? This whole exercise. This whole exercise led me towards what we have seen earlier. It's nothing new. Is that if I have a pair of operators which satisfy this, where number operator is this, you can go from 0th state to the higher states by this, where 0 is nothing but the 0 eigenvalue of n operator. The 0 eigenvalue state of n operator. From there you can go to all the states by applying this formula and applying this. So
These are the operators in this context, not the harmonic oscillator ones.
hello, can you hear me?
Yes, sir.
Yeah, sorry, there's a power cut here. So let me join again and turn up the video because I'm using mobile network. I should buy this. What is this called? This battery or backup for Wi-Fi router. So I bought one, but it was 12 volt, so it was doing some problem. But then I realized I need 9 volt. Then I got lazy for it. So now I have to buy the 9 volt one. Yeah, so that's where it stands. Okay. So what I'm trying to say, so all these exercise eventually led to something which I know already, is that which we know already. Okay, I think the network is not that bad. Which is that just let me know in case my video is slow or something. So this exercise will lead to something which we already know, that if there is a pair of,
What if there is degeneracy in the spectrum of n, the number operator?
what do you mean by degeneracy?
Then that ket 0 is not well defended. There might be other eigenvectors which also have 0 eigenvalue.
No, but we just, the way we define, so you mean to say there are two operators, there are two states, okay? You mean to say there are two states, which is some alpha and some beta, which has the same number, same eigenvalue, right?
Yeah.
So is it possible at all, the way we defined it, or the way we set it up? Can you see that?
Yes, sir.
Yeah, are you following, Ainesh?
So A takes it one step down, then A dagger takes it one step up. So it'll be the same state. Is that the argument?
Yeah, that is the argument. So you not only that the eigenvalue will be just an integer in unique integer label for each state. Okay. So show that. So act in on this in state, whatever it is, right? You will get a unique integer which is this. Okay, make sense?
Yeah.
Okay. So the point of this exercise is there is no, yeah, so there is no degeneracy possible because it's uniquely defined in that way. And the point of this exercise is now you have a bunch of states. Notice that don't mix it with the other problems. You are probably, you thought of degeneracy because you mixed it with an harmonic oscillator problem, because we earlier did this two-dimensional isotropic harmonic oscillator, right? There we have degeneracy. That's the energy degeneracy, right? But this is not that. This is a unique. I am only dealing with the number operator and its eigenstate. Again, I am not dealing with Hamiltonian. I don't know whether it commutes with the Hamiltonian, whether there is a degeneracy possible. That can happen. That's a defined question. The Hamiltonian might have degeneracy. Then it's a defined point. And not only that, when you put multi-particle, then all these questions of energy degeneracy, etc., will come. But that's a different direction. Right now I'm just interested in the eigenstates of the n operator. Okay, so now the states are following.
So this formalism is constructed for our context.
Yeah, so so let's say what was our problem actually. Let's go back to that. Our problem was to develop an object, an operator which will take me between the states of Fock space, right? So I am trying to set up this by inspired by harmonic oscillator analogy. That the commutator, the commuting operator in harmonic oscillator has the property which will take you from these number states. Okay? And now I will use this property for our purpose. Okay? And
Okay.
moreover, we need one more thing which we didn't have earlier, that I described earlier last day. That notice this problem was following, that the Fock space problem was that I have states like this. So let me write it here. I have state right. If there is only two states, infinite particle, let's say. But there can be infinite state, infinite particle, then it's a little cumbersome to write. So we want something to go from here to here to here. In this is actually an infinite dimensional. Right now I'm writing only two states. That's why it's two-dimensional. But if I have infinite states for the full Fock space, then I'll have this infinite dimensional matrix or infinite dimensional lattice. So I want a commuting object between these elements, just like this, just like the harmonic oscillator problem. Right? Just like that, we want something to do that. This is our agenda. And I also want another object which will strictly confine here and not go anywhere else. Let me put it in a different color. Because I know there are anti-symmetric wave function that doesn't go anywhere else. So that is our agenda. That is where we are heading. Okay. Are you following
And
that?
we are borrowing this idea.
Yeah, we are borrowing the idea
Yeah.
from, because we already have an object like that. We are borrowing this idea here.
Just this
What I did so
commutator
far-
and then we're picking.
Yeah, what I did so far is a repetition. You know it already. There is nothing new. Okay, I just repeated stuff. I just revised stuff. Okay, now I'm going to do a little new thing. But so far I have just revised stuff. But why did I do that? Note that why am I doing all this? Because I want an object which will take me to these states. And you notice what what was the speciality of this algebraic method? The speciality of algebraic method of harmonic oscillator was that you can construct the whole Hilbert space just by from the ground state, just by applying it again and again. And we also did this exercise in 2D and 3D harmonic oscillator, where you have more and a little more complicated expression, but the idea is similar. Okay, and then there in that case you had degeneracy with Hamiltonian and all. So I'm not going to enter in that discussion. That's a separate agenda. But here we don't have anything like that, because we just have a harmonic oscillator. We just have this number eigenstate and nothing else. Okay, is the full picture clear? Okay. I sense some discomfort, so you can spit it out. Like, what is exactly the problem? Anyone?
No, I
sense-
mean, this is the thing we have done earlier for SHO, and nothing new has
Yes.
been.
No,
We
nothing
have
new.
not gone
Absolutely not.
into something new. Okay,
No,
that
not
was
yet.
just recap. Okay.
Yeah, sometimes we have to revise stuff. That's why.
Yeah.
So
Okay.
and Ainesh, are you clear about the degeneracy point?
Yes, yes.
Okay. So now this is exactly what you did already. There is nothing new yet, as you pointed out. Okay. And these are nothing but, one is nothing but a dagger 0, 2 is nothing but a dagger 1 modulo this normalization. So let me write it as normalized, etc. Okay. And we use this, we call this n, a dagger a, as number of particles. So now I am coming to a physical picture. So I am calling it a number of particles in a level. To be very precise, I call it boson, number of bosons in a level. So I want to interpret this thing as a representation of a dagger, as a representation of, it creates a boson. Okay, and n particle, take n particle state to n plus 1 particle state. Okay. Note that I am identifying this mathematical thing with a physical phenomena, and I will write down the multi-particle wave function in a moment using that. Okay. So there is nothing wrong in saying that. I am just saying I can put particles in a state and keep putting them in many like that. Okay. So now let's come to the point of another operator, which is if, and that satisfies the property of anti-commutator. Okay. And self one is 0 as usual, like just like the commutators. These are the all this property, where this curly bracket AB implies AB plus BA. So what kind of property it will have? So it will be n. Let's define a n f dagger f, a number operator, and then let's define how does it act on phi. Same exercise. F dagger f phi is some phi eigenstate. So now I act this on both sides, and this is, sorry, why it will be 0. Because it's a square, so it has to be greater than 0, just like before. So phi is so this is nothing but phi. So it's equal to phi. So phi is mod f phi 0. Okay. So that tells me the phi greater or equal to 0. Same exercise, nothing new. And f phi 0 is 0 if phi equal to 0. Exactly same exercise, nothing new. Now let's see where something new will happen. So this operator will have the unique property that if phi is 0, right? So that means, so I can write this f dagger phi also, because f and f dagger, if I reverse it, they will be the same thing. So now this operator is nothing but phi f dagger phi. right? If I write open the square. Now notice that f dagger plus f dagger f is equal to 1. So that means this guy is phi 1 minus f dagger phi. Okay. So that means this is 1 minus phi because this object is nothing but phi. That's what we have seen here. But that means that since
So it will be, I think, f dagger f means 1 minus f dagger f.
what
Previous line 1 minus 5 above it.
if
You wrote
yeah
1
correct
minus.
yeah correct. Okay, good that you are awake at this morning. Very good. Okay, so that means this quantity has to be greater than 0 because it is a square. So 1 minus 5 must be greater than 0. It means 5 must be less equal to 1. So that means I land on this property because of anti-commutator that 5 must be 0 to 1. This didn't happen before. Okay? Earlier 5 was totally unbounded. Only thing was it is bounded at the bottom at 0, but now it is bounded at the bottom and top. Okay? So now let's see what does it mean. Now it is almost obvious that what is going to happen then, because earlier I was going like that, applying a dagger and going up. But now I am starting from 0 and 1. That's it. I cannot go anywhere else because it is bounded from top and bottom. So this anti-commutator implies you have only two possibilities, either 0 or 1, only two states. So let's stretch it further and see. It's already obvious. I'm just showing you f dagger f phi is 0. So f phi is obviously the null vector. So it is either null vector or f phi is the 0 eigenstate. Okay. So now let's try to see. So this is actually a very simple exercise. You can show it yourself also. If phi equal to 0, only if phi is equal to 0. Okay. So from that implies that that 0 is an eigenvector of n. Okay. Okay. So now further exercise in f dagger f 0, not f dagger f, sorry. Now I want to see where does this f dagger takes us. Okay. Now we know that it is f dagger f dagger 0. That means I can use the anti-commutator. So f dagger is 1 plus f dagger f 0, and that is equal to f dagger 0. So that means f dagger 0 is proportional to 1. So this is an eigenstate of n operator with eigenvalue 1. So that means it is proportional to 1. And similarly, I can do, so I'm just skipping couple of steps because I think it's just a lot of algebra which you have to sit down and do. You can show that f dagger 0 mod square will be equal to 1. Show that. All you have to do, you expand this, write it as f dagger and use the anti-commutator 1 plus f dagger f. And then you can get the 1 and show the other part is obviously 0. So that means f dagger 0 is 1. No hassle of the normalization. So now we got a two piece of equation which is very simple. One is f1 is 0 and f dagger 0 is 1. That means I have two states 0 and 1. I go here by f dagger and I come back here by f. That's all, nothing else. Okay? And f dagger 1 is f dagger 1, and using the double empty commutator you can show this is 0. That means, so notice, so everything is clear so far, at least this. If you have not followed the sub algebra, did you understand this statement? Everybody is clear up to this? Any comment? Am I connected? Okay. Now what about this? Did you understand that f phi is 0? It is exactly an analogy of previous argument. And nf dagger is 1. It's a, there is nothing new in this argument as before. Is everybody clear up to this? Okay, your internet is poor.
Sir,
So in that case, you have to look at the recording. Yeah.
sir, you said earlier that either phi 0 is 0, or and then you said that instead of calling it properly 0, we are saying that it is a 0 state. So here
No,
also
what do
we
you
are
mean by I
saying
didn't follow? Instead of calling it properly 0 means it is 0.
no, properly 0
Oh,
means
you mean
instead
to
of
say I am
calling it
null
0,
vector or eigenstate of n?
yeah, yeah.
Yeah,
So here also
yeah,
you
yeah.
are doing the same. You are saying that instead
Yes,
of
yes,
calling it to
exactly
be
same
0,
thing.
we are saying that it is a 0 state.
Hmm.
Okay.
Right. So there. So I'm not calling it a 0 in that sense. I'm calling. And you get it's an eigen. Okay. Okay. What is the problem? I see some comment about internet connection, right?
Your voice,
Is there a lag?
yeah, you couldn't hear anything.
Okay, so let me switch to the Wi-Fi. Hello? Can you hear me properly now?
Yes, sir.
Okay. So I just switched from my mobile to the Wi-Fi. The current is back now. So now notice in all this exercise, we exactly got what we wanted. Okay. So this is exactly, if I identify it as number of particle, so this is exactly what we want for fermions. One for antisymmetry fermions or a function of fermions. Mhm.
So can you please repeat what did you say about A acting on this 0 equal to 0 and A acting on 1, 1, 1?
Sorry, what? Say that again.
That part A acting on 0, 0 states is equal to 0
A
and A
acting on,
acting on
yeah. So
that,
I'm just
yeah,
saying
at the left hand side.
so I am saying these things in the sense of a non-trivial vector, not a trivial zero vector. So if I can always have a trivial zero vector, which could mean that it is some zero state. Okay. So what I'm trying to say, I'm trying to find so when I trying to say this is a zero eigenstate. Okay. Now zero eigenstate could be either of this or this. So this is a trivial null vector and this is a non-trivial null vector. So it's a generic property of any matrix. So when I'm referring to it, I'm just calling it's a null vector that satisfies this. So then I am calling it as a non-trivial vector which satisfies this property. Okay. Yeah, because of course you can write it as a everything is zero. Then it's a trivial property, the trivial vector. So now let's use all this idea to get what we are looking for. Okay. So now notice we describe our Fock state eigenkate, a Fock state kate as nk, which is n1, n2, n3, something like this. Okay. So let's say it's a boson or symmetric wave function. So this thing I am referring to as nk. Okay. And I can write this can be anything. Like this could be if there is zero particle, no particle nowhere. So then it will be 0 0 0 0 0. If there is one particle in the k state, it will be 0 0 0 1 in k state and again 0 everywhere. Right? So this is the generic representation of my bosonic Fock space. Now I want to define this operator bk that acts on nk and gives me square root nk. It kills a particle from the kth state, and the square root is required because we described the normalization. And bk dagger does the following. So let me use these two operators, which must satisfy the property that bk dagger commutes. Okay. So how to check that? You can check that very easily. You apply bk dagger bk on this state, and you get the act of bk will give you root nk, right? Root nk bk dagger nk minus 1 dot, dot, dot. So now you can act a bk dagger using this definition. So that will give you nk minus 1 plus 1 root nk. Okay, so this is nk will cancel and you'll get nk. So this is one more thing to notice. This is the number operator. So it will give you the number of particle in the kth state. Okay. So similarly, I can act bk dagger. Okay. So do this exercise. You will get nk plus 1. So notice this one is not a suffix one. This is a full one. Or sometimes I'm writing in a little casual way. So that
Sir,
means
are you writing anything?
yes. Is it
It is
lagging?
not visible, means we cannot see.
Okay. I'm writing a lot of things. Wait, let me switch there also. How come it's not showing like it's showing to me in real time? Can you see what I've written now?
Yeah, now can see that
From
P
where
dagger,
you stopped
PKB
following?
dagger.
Did you
This
see
last
this
point you,
box? This
yeah,
box?
yeah. In
Okay.
the in cap operator was also visible. The last point only.
Oh, okay. So I'm just showing that bk dagger is 1. Okay. So in order to do that, I use the bk dagger bk and I got nk, which is like the number operator, and bk dagger gave me nk plus 1. So now simply I can subtract them and show that bk dagger minus bk dagger bk acting on this state nk will give me 1. Okay. Now do a little bit of work and show this. So this is something I have already shown you. This is I have already shown you. Now show this. Okay. Now let's see that what is the structure of this Fock space. So the structure is following then. So let's now look at the example that now it gave me everything I wanted. So let's say let's go back to these two particle states or two state many particle thing. So what will these give me? Can somebody tell me what will this give me according to this definition? This is position 1, this is 2, like k equal to 1.
0, 1.
It will give me 0, right? It is a null vector,
Yeah.
or it's the ground, it's a vacuum. Now what will this give me? So,
0, 2.
0, 2.
right. Okay. So B2 dagger, I actually wanted to write this B2 dagger 0, 0. This will give me 0, 1. There is a normalization, of course, which I am not writing. Okay. So now, can someone say what is this? Someone else other than you?
So here will be a zero vector. And I doubt, sir, like the zero vector is not the vacuum, right? Vacuum is 0, 0, 0, etc. Right?
Yeah, but I am saying let's say I have only two states. I'm
Yes.
just giving you a simpler example, right? So B2 dagger will give me 0, 1, but B1 will ruin it, right?
Yes, sir.
Okay. So this way I can now, I have got a connector between all the states. So let me now put this thing in a lattice.
Sir,
Yes.
yeah, you applied B2 on 0, 0 state. So
Yes.
0, 0 state was already vacuum state. So
Yeah.
is it the can I say that I am applying B2 on the vacuum state and it is uh, giving me 0? I mean,
Yes.
the vacuum state is being destroyed or something like that.
Yeah. So that is how we defined it, right? This operation will not take you anywhere. You cannot do this operation, right? So this is the same debate we had earlier. So it means that it is just like here, right? Just like the way we defined it.
Oh,
F
okay,
phi is
okay.
equal to 0, right?
I
It is
I
exactly
remember.
the point where I was also confused earlier.
Yeah.
Okay. Okay. So let's say now let's navigate between in this space. It's a two particle, two state, okay? Because ideally I should write it infinite, but I cannot write it in this 2D plane. So that's why I'm making it two state. And so on, right? So now this Rukmini wanted to always go like this. So how will I go from 0 to 1? Okay, I can go in this way. Okay. So if I go in this way, I first act a B1 dagger and then I act a B2 dagger. So 1, 1 is proportional to right? Or I can go in this way also. They are equivalent because they commute. These two operators commute. Right? Or I can be a little sadistic and go like this. Here. Right? I want to go from here to here. And that will be 1, 1 will be first B1 dagger, then no, this is B2 dagger. So first B2 dagger, then B2 dagger, then B1 dagger, then B1 dagger, then going down. So that means B2 and then going back. So B1. Okay. This is also a legal way of writing this state. Okay. So now you understand that now I can go anywhere to anywhere in any different ways. I can go by creating annihilating particles and go from one state to another state. And I got the connector I wanted, which allows me to go any state to any state in different possible ways. So this path is not unique. Path can be anything, and I will come in a moment in the next class what does that physically mean. But the main point is you can do this. Okay. Now one more thing I want to just state and finish this lecture, and you internalize this point slowly for one day. Then the fermion has the additional thing that the fermionic lattice is just this. You cannot go anywhere. Okay, that's all, nothing else. And it should have the property that if you go in this way and if you go in this way, there is a difference of minus sign. So convince yourself this point, then I'll come back to it and I will show you how to write down the fk. Because there are only two possibilities, there is no n. Try to think how will you write these two, just like the way you wrote this. Okay. Any confusion so far about how this thing is allowing me to achieve what I wanted, which means a connector between creating the Fock space by applying this operator again and again. Question, confusion, everything is clear?
So could you repeat once more about how the number operator acts on vacuum to give the same vector?
Yeah. So no, not same vector. It gives you the zero vector. Oh, number operator. Okay. Right. So number operator acting on 0, 0 will give me 0. Right? Because there is no particle. So what is your question? That is the property of the number operator. That is what we showed, right?
I thought we told that it's an eigengate.
Yeah, it's an eigengate, but zero eigengate. That is what I'm trying to say. Zero eigenvalue eigengate.
How is there an eigengate like that?
Sorry, I am not following.
So how is there an eigengate like the zero eigenvalue means?
Yeah, so I am not getting your question. You are not completing your sentence. So what do you mean by how is it a zero eigenvalue eigengate? This is the meaning of a zero eigenvalue eigengate.
So my doubt is, so in this whole Fock space thing, like we write the state such that the ith position we have the nk ith eigenvalue, right?
No, it's the eigenvalue of the number operator. Yeah.
Yes, so if I have 0 as eigenvalue,
Yes.
then would I'm not going to write it as like the Fock space element is 1, 0, 0, etc., right?
I'm not following your statement at all.
So like an element in the Fock space would look like the ith element from the left would be, if I have one over there, then that would mean that I have one particle at that eigenvalue.
No, one particular eigenvalue. No, that doesn't mean that. So if you are trying to say if I at the ith position you have 1, right, and 0 everywhere, right, that means you have one particle at the ith position. So if you act ni, then you will get 1. But if you act nk, then you get 0. Right? Are you following?
Is I'll check into it.
Yeah, you can write down this question more clearly in Piazza perhaps, because I'm not following what are you saying. If you write it down, perhaps it will be clear. Now there is a quiz. I think it is already online, and since it is a bit late, 4 minutes, so I'll add 4 minutes into the submission time. So it's 10-minute quiz, but I mean it's already up, but you can take 4 extra minutes. 4 extra minutes in the sense that the submission time is given 9:35. You can submit it till 9:39. Okay. Let me just check if the quiz is up. Can everybody see the quiz?
Yes, sir, it's up.
Okay. So So write down this question because I'm not following what are you saying. If you write down, perhaps it will be clearer.
Yes, sir.
Yeah. Let me change the submission time. Okay, I guess that's all for today. And so go over this algebra, internalize it. Then I'll come back again and repeat the interpretation that how it is helping us to achieve what we want. But make sure the algebra is in your grip. Okay.
Sir, do I have to explain the questions?
Yeah, that is what I wrote, no, in the comment. So you can
In
either
private comment.
either private comment or an upload, whatever you prefer. If you are
Okay.
writing it somewhere, you think, and I think these are 2-line answers, so you
Okay.
can, yeah.